The next thing we are going to do is to talk about how you form vectors from scalars. In particular, I would like to talk about the cross product of two vectors, but we need a few preliminaries before that, and one of them is this issue of coordinate frame or systems other than Cartesian coordinates. So let us again look at the simplest example, which is a two-dimensional plane, and look at what we already know from elementary geometry, which is the following. On the xy plane, the position of any point here is given by a position vector r, which comprises, in terms of unit vectors along the x axis, which I believe is denoted by I in standard notation, and along the y axis by j. The idea is to write this as x times I plus y times j, meaning that you go x units multiplied by I, the unit vector in the x direction here, and y units here, and the resultant of this vector plus that vector is indeed this position vector. So that is the standard way of writing this, but I will often write this also as just x comma y, or sometimes depending on what I want to do, I write it like this. They are all equivalent ways of writing the position vector of a point in two dimensions in a plane. Okay. Now this is not the only way in which you can describe the position vector of a point. You could also say, well, why don't I write it in terms of this distance from the origin to that point and the angle made with respect to some reference direction, conventionally taken to be the positive x axis. So if I call this angle phi, for a reason which will become clear when we go to 3 dimensions, I do not want to call it theta at the moment, because I reserve theta for another coordinate in 3-dimensional space. So if I call this distance r, in fact I should use another symbol for r itself, but does not matter, it is a position vector in a plane and a phi here. I could as well tell you what this distance is and what this angle is measured from here in the positive sense, and then the position vector, the point here is uniquely specified. So the coordinates of any point in a plane can either be written down by telling you what its Cartesian components x and y are, or what its plane polar components r and phi are, and it is immediately clear that r squared is related to x and y by r squared is x squared plus y squared, and similarly phi, or rather tan phi, is equal to y divided by x. In other words, the tangent of this angle is the perpendicular divided by the base in this fashion. So if you like, r is defined as the positive square root of x squared plus y squared, because it is a distance and it can't be negative, and phi is given by this quantity here. Then the question arises as to what are the ranges of these quantities. Just to remind you, minus infinity less than x or y less than infinity. So that is the range of the original Cartesian components on a plane running all the way unbounded both directions. On the other hand, 0 is less than equal to r less than infinity, because this distance can at best be 0, at the least value is 0, and on the other side it is unbounded, and phi runs 0 less than equal to phi. Phi is 0 means you are on the x axis, the point is on the x axis and goes all the way up, all the way around up to 2 pi, but 2 pi is identified with 0 because you are back at the same point. So I should really write this as less than 2 pi, so that the coordinate is single valued. So these are the transformation rules from the Cartesian to plane polar coordinates. So theta r and phi are called plane polar coordinates, and these are the forward transformation rules. You give me x and y, and this is how I find r and phi. So this is tan inverse of y over x. In this range. So you choose that branch of tan inverse y over x, which is in the range 0 to 2 pi. Going in the other direction, given r and phi, what are x and y? Well, remember this is x and this is y. X divided by this magnitude r is of course cos phi. So it immediately follows that the reciprocal relations to these two are x equal to r cos phi and y equal to r sin phi. So you have either this set of relations going from Cartesian to plane polar or from plane polar to Cartesian via this transformation here. Now whenever you have such a mapping from one set of coordinates to another, it's the same plane that we are talking about but two different descriptions. There are some things called mapping singularities. For example, the origin, the point 0, 0. The value of the azimuthal angle phi is indeterminate. R is 0, that is the point at the origin. The origin is specified by simply saying r is 0 and there is no meaningful value of phi. It is indeterminate here when x and y both go to 0. So this is just a harmless singularity at this level, but it is there. One should remember that it is there. For all other points we have a unique phi and a unique r, subject to this modulo 2 pi restriction here. Okay. Now what about the unit vectors? Well, this is the interesting point, because if you have a point here, I can still define a unit vector in the x direction, it is I, and a unit vector in the y direction, that is j, and they do not change as I move from one point to another. This one is parallel to the x direction, positive x direction, and that the parallel to the positive y direction, and that is it. And we know that I and j are perpendicular to each other, and they remain so everywhere, and they are independent of where you are. So if I were to ask what is the basis, the Cartesian basis vectors at this point, it would be this and this, or at this point it would be this and this. But I can have another set of unit vectors, and here is where we start needing a proper notation. I would like to use another symbol for the unit vector, which is e, little e, with a subscript to say in which direction it is or which coordinate it refers to. So from now on I am not going to use I and j, but instead I am going to write r as x times e sub x plus y times e sub y, to remind myself of the fact that this quantity here is what we call I and this is what we call j, and this is to remind myself that these are unit vectors in the x and y directions respectively. Okay. What would you write for r in terms of a unit vector in the radial direction? Well, the magnitude here is little r without a vector symbol, and the direction of this position vector is this. So there is a unit vector here, and let me draw a neater figure. So for an arbitrary point at distance r, there is a unit vector in this direction which I should call e subscript r, a unit vector in this fashion. But to define the position of a point on a plane, I need two pieces of information. So I need a linear combination. I need the coefficients x and y for two mutually perpendicular vectors which form a basis in this plane. Well, actually you can use oblique axes also, but right now we are talking only about basis vectors which are perpendicular to each other. This is the simplest case. So I need a vector at right angles to this, and since this is the direction of increasing phi, this vector here is a unit vector in the azimuthal direction, increasing azimuthal angle. So remember that this phi, the polar angle in plane polar coordinates, is also called the azimuthal angle. And this unit vector here is e subscript phi. Okay. And now I can write down what this r is in terms of these unit vectors. Remember that the physical dimensions of r are length. So you have to on the right hand side have a length. These things have no dimensions at all. They are unit vectors. This quantity here and this quantity here, each of them has a dimension of a length. And of course the vector r is the vector that starts here and ends here, points in this direction. So it is equal to the magnitude little r multiplied by a unit vector in that direction So it is equal to E sub r and nothing else, and nothing else. It would be incorrect to write something like E phi. It would be incorrect. It is dimensionally wrong in any case and you do not need it. It is not there. This already tells you what the position vector r is. So therefore, this is a crucial point. If you write this in plane polar coordinates, then the radius vector to any point is just the magnitude of the radius vector, which is the distance from the origin, times the unit vector in the radial direction. That is this quantity and that is it. Okay. But here comes the catch, here comes the point. If you go to some other point and ask what is the unit vector, it is equal to E sub r here, and the azimuthal vector is going to be E sub phi here. Unlike Cartesian coordinates where the unit vector here was the same as the unit vectors here, they were just transported rigidly from there to there and therefore are coordinate independent. That is not true any longer. Both ER and E phi are dependent on where you are. So you should really write this as ER of r comma phi, E phi of r comma phi. This is a characteristic of using coordinate systems other than Cartesian coordinate systems. Except for the Cartesian coordinate systems in any dimensional Euclidean space, all the other coordinate system will have unit vectors which are position dependent, which has of course advantages as well as disadvantages. The advantage here is I can write it down very simply in this fashion, but the disadvantage immediately is that this is position dependent. Therefore, for instance, if you are going to describe the position of a particle which is moving in this two-dimensional space in this fashion, at this instant of time its position is out there and this is the radius vector with a radial direction like that. At a later instant of time it is here with a position vector here, the unit vector in that direction. So the unit vector also changes with time as the coordinates change with time, and therefore if I am going to compute velocities and so on, I must make sure that I also take into account the variation of this with time, the unit vector. This is going to be important and it is going to prove to be an advantage as we will see later on. But I hope this is clear that the unit vectors in the Cartesian system are in some sense rigid, they are fixed once and for all, independent of the coordinate or the position of the particle, but the unit vector in any other non-Cartesian system immediately is position dependent and we have to take that into account at all times. Okay. Having said that and talked about plane polar coordinates, we will go back now to two-dimensional vectors or vectors in a plane and discover what kind of scalars we can form from it, from vectors, and what kind of vectors we can form from it. So once again let us go back to this dot and cross products of vectors. Okay. The simplest of course is the original dot product with which you are already familiar, and we are talking for the moment in 2 dimensions. So two-dimensional space, the xy plane if you like, so xy always. In this space if you have a vector A and it has got components a sub x and a sub y, and another vector B which has got components b sub x and b sub y, then the question that we can ask is, can we form scalars from these vectors? We have already seen how to do that in the simplest case. I already pointed out that ax and ay transform exactly like x and y under a rotation, arbitrary rotation keeping the origin fixed, and that ax squared plus ay squared is unchanged, it is a scalar. So the rule of the game is that a dot a is defined as ax squared plus ay squared. So you take this fellow, square it, you take this fellow, square it, and this is, if you like, the square of the magnitude of this vector A. and that is a scalar. We have seen that already, that is a scalar explicitly from the fact that x and y had those trigonometric transformations. Okay. Similarly for b, we have b squared equal to b dot b, and it is conventional to write this as a squared equal to this without a vector symbol, and this guy here is bx squared plus by squared. This is a scalar, that is a scalar here. But now again using those trigonometric transformation laws, it is not hard to see that ax bx plus ay by is also a scalar in exactly the same way, and this is written as a dot product b is defined as ax bx plus ay by, okay, and this is a scalar. So the dot product, which puts a dot between two vectors, is also called a scalar product, dot or scalar product. The dot product of a vector with itself, which is the square of the magnitude of the vector, is a special case of the more general definition that you give me any two vectors and then I form a dot product between them by multiplying similar components, like components. So ax with bx, ay with by, I sum over this, sum the two of them, and I get a scalar quantity here. So that is one way of finding a scalar from a vector. Okay. If therefore you had 2 points in space and one of them had coordinate r1 and the other one had coordinate r2, I could ask what are all the possible scalars you can form from r1 and r2, independent scalars, functionally independent scalars, and of course be r1 squared, r2 squared, and r1 dot r2. Now what is the geometric meaning of this quantity here? Well, here is my coordinate system, here is my vector A, there is my vector B in this fashion, and the angle between them, let us say, is theta. Then resolving A as ax cos whatever this angle is plus sine whatever this angle ay times sine, and similarly for B, it is a trivial matter to show that this quantity is also equal to A times B times cos theta. And you can do this very easily by writing down the transformation rules or some elementary trigonometry to show that A dot B is the same as AB cos theta here. So here is a quick way, instead of doing this, which is a little messier, a quick way of finding the dot product of two vectors is to take the magnitudes of the two and multiply them and multiply the result with the cosine of the angle between them. Okay. Now that leads to an important and very, very interesting identity, if you like. It is called an inequality. It is quite clear that, by the way, this is the magnitude of A, this is the magnitude of B, and it also says that cos theta here is an angle which runs from 0 to whatever pi or 2 pi, and the magnitude of cos theta is always less than equal to 1. So it immediately tells you that the magnitude of A dot B, which is a real number which could have both signs, because when theta is in the second quadrant or third quadrant and so on, it is negative. So this quantity could actually be negative. There is nothing which says that this should be a positive quantity, because these individual components could have either sign, positive or negative. So it also says that if you took the magnitude of A dot B, this is equal to A times B times the magnitude of cos theta, because A and B themselves can't be negative, they are magnitudes of vectors, and this is less than or equal to A times B, because the magnitude of this is less than or equal to 1. Okay. And this is a very important inequality. It has got many names. At this level it is called the Cauchy inequality, because and it simply at this level expresses the fact that the magnitude of the cosine of an angle cannot exceed unity. It has got to be between 0 and 1, including of course the end points. Now the simple question is, when does it become equal to AB? When does this become equal to AB? Obviously when the magnitude of cos theta is equal to 1. And when does that happen? It happens either when A is out here and B is out there in the same direction, so theta is 0, or when A is in this direction and B is in this direction. This would correspond to theta equal to pi, and this would correspond to theta equal to 0. So what does that mean? That implies that B is either parallel or anti-parallel to the vector A. In other words, B is some number times A, because that number could be negative if it is anti-parallel and positive if it is in the same direction, if it is parallel. So it says B is not in different direction in the plane, but A and B are collinear. As soon as two vectors are collinear, then the magnitude of the dot product becomes equal to the product of their magnitudes on this side. So this is a very important observation, and it generalizes to other dimensions. It essentially says that when two vectors are linearly independent of each other, namely one cannot be written as a product of number times the other vector, plus or positive or negative number, then this inequality strictly applies, and the equality applies if and only if the two vectors are collinear with each other. That is a very important observation which has got many generalizations, including the uncertainty principle in quantum mechanics. So it finally arrives from a generalization of this simple observation here. Okay, so now that we have this elementary thing done, let us look at what else we can do with these two vectors. The other thing we could do, and incidentally I need a little bit of more elegant notation because I am going to talk about this in higher dimensions, and we will come to that in a minute. I have two quantities here and two there, these two vectors. I could form the following combination. I could form Ax by minus Ay bx and ask, what does it transform like? What does this quantity transform like? I know the transformation for Ax and Ay and bx and by. Now what does this combination, bilinear combination, look like? Well, incredibly enough, this quantity also looks like a scalar. This also appears to transform like a scalar, but it is not the same scalar as the dot product. This guy here, A dot B, was equal to Ax bx plus Ay by, but this also transforms like a scalar. But it is not the scalar product, it is not the scalar product, and it looks like something part of a more general structure of some kind, and because it is two dimensions it is a little deceptive. It appears in this very simple form, but this has got a meaning here which will become clear after we talk about what happens in 3 dimensions. It turns out that this quantity is the analog of the so called vector product or cross product in 3 dimensions, which produces a vector out of 2 vectors by a certain prescription. In the case of 2 dimensions, you do not have enough components, you have only 2 components, and therefore the same prescription leads you to a single quantity of this kind, and it turns out to be a scalar in this case. But it is not an ordinary scalar in this case, and let me explain what is happening here. If for instance you said, instead of a coordinate system which behaved like this, instead of rotating this coordinate system, suppose I said I reflect this coordinate system about one of the axes. So my new axes x prime and y prime, if I reflect about the y axis, then this is what my new axis would be, x prime, but y prime would be the same as y because I am just reflecting by putting a mirror here, so this axis gets reflected to this side. Okay. Now this coordinate system cannot be obtained from this coordinate system by any rotation, because the moment you rotate x to bring it to this side, y also rotates downwards out here. So this is not a rotation, this transformation is not a rotation. The transformation here is to say that if I had a point out here, this point in the new coordinate system, this x and y would go to x prime y prime, which would be equal to minus x and y. So the x coordinate gets reflected, but the y coordinate does not change at all. Now this too is not going to affect your definition of a scalar, because the distance from the origin does not change. X squared plus y squared is the same as minus x the whole squared plus y squared here. So what's really happening? What's happening in this case is that one component changing sign in two-dimensional space is not a rotation, is not obtainable by a rotation of the axes, and then a transformation of this kind is called an improper transformation as opposed to a proper rotation here. And now what we will see next is that while this quantity has specific transformation properties under that kind of transformation, does not change, this kind of quantity will change, it will in fact become minus itself, and therefore this is not quite a scalar, it is a sort of pseudo scalar, and the word in fact is pseudo scalar. So even within scalars we have a little bit of sub classification depending on what these quantities do under rotations and improper transformations like reflections, which too are valid transformations, because when we say the laws of physics should not depend on how you orient your coordinate system, they should also not depend on whether you choose a coordinate system which is right handed or left handed, it should not matter. So as long as that is true, you need to be able to deal with quantities which also have specific transformation properties under these improper transformations, and here is one such example. We will come back to this because this will become much clearer after we talk about what happens in three-dimensional space. So the next task is to go to three-dimensional vectors and ask what are the possible kinds of multiplications of vectors that you could have and how do they transform among each other. So just to remind you once again, when we talk about 3 dimensions, we are going to get something called a vector product or a cross product of 2 vectors, but it will turn out that the analog of the cross product in 3 dimensions in the case of 2 dimensions is something which produces really a scalar and not a vector. So to cut a long story short, the idea that the cross product of 2 vectors produces another vector is specific to 3-dimensional space. It is not true in 2 dimensions, it is not true in any dimensionality higher than 3, like 4 or 5 or 6 or anything like that. So this is a peculiarity of 3 dimensions, a very important peculiarity, and we will see what role it plays in whatever we are going to do. So we will talk next about 3-dimensional vectors and how to find quantity which transforms like a vector when you take 2 vectors and combine them into what is called a cross product. So that is the next task.